Today, I want to look at light. This summer, I've been spending a lot of time around pools, and I noticed something interesting. Light creates strange patterns at the bottom of pools. Notice, if the surface of the pool is mostly level, nothing interesting happens, but when I disturb the surface, all sorts of things happen. There's lines where the light is very bright, spots where it's almost completely dark, and then there's spots where almost nothing seems to change. The idea behind this is pretty simple. There are spots where the surface acts as a lens and focuses the light down to a point, and also spots which do the opposite and scatter light away. But that's not good enough for me. I want to know exactly what the bottom of the pool will look like if I know exactly what the surface looks like. In other words, if we have a function for the surface of the pool. Let's start by simplifying the problem. Let's look at the case where light comes straight down onto the surface of the pool. When a ray of light hits the surface, Snell's law tells us that that ray of light is going to bend by some amount. When this happens, that ray of light takes a new path to the bottom of the pool and hits the bottom at a different point than where the light originally entered. Essentially, we're saying that the light hits the surface at the point xy and hits the bottom at the point uv. As an added side note, we're going to assume that each ray of light maps to a unique point at the bottom of the pool. In other words, no two rays of light can hit the same point at the bottom. In physics and math, we call the idea of shifting from one point to another point a map. So, to read from our problem, we can say that the surface of the water maps a point xy on the surface to a unique point uv at the bottom. This idea of a map comes up all the time in physics, namely with fluid flow. In a fluid that's flowing, points map to different points which are further downstream as time progresses. And what's interesting is that what we're going to look at here with light applies almost seamlessly to how we would describe the density at points during a fluid flow. But let's not get sidetracked. Let's shift back to the idea of maps. More specifically, let's look at ways to visualize maps and intuitively understand what maps actually do. A good way to look at maps in one dimension is to look at a number line. If we just look at a number line for x values, the tick marks are evenly spaced. But if we look at a number line for u values, the tick marks get shifted a bit. And importantly, the spacing between the tick marks changes. So maps don't just move points, they also stretch or squish units of length. And that's an important fact to remember. Let's now look at two dimensions, since after all, that's the case we're dealing with when it comes to our light problem. Well, instead of looking at a number line, let's look at a plane full of grid lines. Just like the one-dimensional case, the x and y values are evenly spaced, filling the plane with a bunch of identical squares. But when we look at the u and v values, the grid lines become curvy and create a bunch of weird shapes in between them, much different than the neatly tiled squares we saw with the x and y values. In a similar way to how the one-dimensional case squishes and stretches units of length, the two-dimensional case squishes and stretches units of area. But what's important is that when we distort the area, the same number of light rays still pass through it. So regardless of whether it's a square or a big blob, the same number of light rays pass through that shape. That means that a change in area just changes the density of light rays. In physics, we call this density of light rays the intensity of the light. In other words, if we have a high concentration of light rays, the light is more intense, or brighter. But if we have a low concentration, the light is less intense, or dimmer. To summarize, the intensity can be thought of as the number of light rays per unit area. Let's write this idea down as an equation. Well, we already said that regardless of whether the shape is a square or a blob, the same number of light rays pass through that shape. But the number of light rays can be thought of as the intensity times an amount of area. This lets us write down a helpful equation. We end up getting that the initial intensity times the area of an initial square at the surface is equal to the intensity at the bottom of the pool times the area of whatever shape is formed at the bottom. But I kind of lied there. What we actually want to look at are small segments of area, and look at what happens when those segments get very small. So instead of writing A for area, I'll write delta A to remind you that what we're really looking at are small segments of area that get infinitely small. But before we start working with this equation, I want to introduce one more. I want to introduce a function which we'll call f for now, which tells us the ratio of the area of the blob at the bottom to the area of the square at the surface. We'll go more into how to calculate this later, but for now, let's just write this as delta AB over delta AS. And keep in mind, this is a function of x and y. In other words, the surface of the water will change areas by different amounts depending on what part of the surface we're looking at. Well, with this function, we go back to our first equation and start rearranging things. Our end goal is to find a function for the intensity at the bottom, so let's isolate that by dividing out by delta AB. If we collect the delta A terms, we can see that it looks a lot like the function f that we just defined, except that the delta A terms in the numerator and denominator are just flipped. So we can write that the intensity at the bottom of the pool is just the intensity at the surface divided by that function f. And what's so great about this is it reduces our problem to just figuring out how to calculate the function f, which is something that we can do fairly easily. But before we do that, let's go back to our idea of a map and write it down in more mathematical terms. When we looked at a map earlier, we said that the map takes a point xy and moves it to the point uv. And while this may sound trivial, different choices of x and y lead to different values of u and v. This means we can write u and v down as functions of x and y. And keep in mind, all this says is that at different choices of x and y, u and v can change, which is exactly what we said before. With that out of the way, let's go back to our main problem, which is finding out how to calculate the function f. Just like when we first started looking at maps, let's go back to the one-dimensional case. We said earlier that maps in one dimension scale units of length, but what's the scaling factor here? What I want to look at is a small change in length. Let's call it delta x. When we apply the map, this change in x gets either stretched or squished to a different value. And since the map brings us into u coordinates, the change in x got scaled into a change in u, which we'll write down as delta u. But what we really want to know is how much bigger or smaller delta u is compared to delta x. So let's divide them, leaving us with delta u over delta x. Those of you familiar with calculus may notice that this quantity approaches the derivative of u with respect to x, as we let the change in x get very small. If we move the delta x to the other side, we get an approximation for just how much u changes when we change x by a small amount. This result is very important. It tells us that changing x results in a change in u, and the amount that u changes depends on the derivative of u. Now we're ready to look at the two-dimensional case, where we're going to look at our two vectors. One of them we'll call x, and the other we'll call y. What these vectors represent are respective change in x and change in y. So we can write these vectors as x equals delta x, 0, and y equals 0, delta y. Now let's see what the map does to these two vectors. When we apply the map to the vectors x and y, we get two new vectors, which I'll call x prime and y prime. If we just look at the vector x prime, we know it's going to get a u component and a v component. But just how big are these components going to be? Well, look back at the one-dimensional case. We know that a change in x gives us a change in u, and we also found that a change in u is approximately equal to du dx times the change in x. This result gives us the u component for the vector x prime. It's just du dx times delta x. Doing the same for the v component, we get that the v component is just dv dx times delta x. And for the vector y prime, all we have to do is swap out the x's in the vector x prime for y's. But why are we even looking at vectors in the first place? The reason is because linear algebra gives us a convenient way to calculate the area between two vectors. And by the area, I mean the area between the parallelogram formed by the two vectors. To calculate the area, all we have to do is put the components of the vectors into a matrix, and then take the determinant. If you don't trust me, do this for the original vectors x and y. When we put their components into a matrix and take its determinant, we just get delta x times delta y, which is the initial area between the unmapped vectors. And we already have a name for this value. This is just delta as from the very beginning. Now, delta AB, which is the area between the vectors x prime and y prime, is the determinant of the matrix with those components. These two determinants let us calculate the function f, which we were trying to find. But remember, the function f is what we get when we divide delta AB by delta AS. But we know what those equal now. Plugging in the two determinants and doing some algebra, the delta x's and delta y's cancel out completely, leaving us with our function written as a determinant of derivatives. This function, which we called f for so long, has a name. It's called the Jacobian, named after the mathematician Carl Gustav Jacob Jacobi, and is often written as j of xy. This function tells us just how much areas scale in a small region around a point when we apply a map, which happened to be useful for our light problem. But like I mentioned before, it's definitely not its only use. For example, one of its most common uses is in calculating double and triple integrals, as it allows for more complicated changes of variables. This function is what I want you to take away from the video. Sure, the light problem is cool, but you may have noticed I never really answered the question, since I never found the functions for u and v. Doing so requires quite a bit of geometry and physics, but it isn't impossible, and I'll leave this as a challenge. If you don't want to go through the math, here are the functions. And you can play around with the concept in a Desmos simulation I made. But that's not the key takeaway. The key takeaway is the Jacobian itself, which tells us just how much areas change when we apply a map to them, something that's surprisingly useful time and time again.